Hello everyone. All right, welcome to another video. All right, today we have this very nice question to demystify. And this time we have a question about energy transfer. Okay, that's the transfer of energy, Now, so we have the question reads, a class of 10 students taking an exam has a power output per student of about 200 watts. So it means the power output per student is 200 watts. But in the class, there are 10 students taking the exam. So assume the initial temperature of the room is 20 degrees Celsius. So which means the temperature of the room is 20 degrees Celsius, and its dimensions are 6 meters by 15, that's 15.0 meters by 3.0 meters. So that means the dimension of the room, just like the volume, okay, the length, the width, and the what, and the height, okay, is given in the dimension 6.0 meters by 15.0 meters by 3.0 meters. Okay, now what is the temperature of the room at the end of 1 hour if all energy remains in the air in the room and none is added by an outside source? So which means the energy in the room, okay, remains, that is, the energy remains in the air in the room. So there's no external, that is, there's nothing like, in what we call thermodynamic system. In thermodynamic system, we have the system, okay, this is the boundary, okay. So everything that happens within the system, okay, we have the thermodynamic process. It happens within the world, the system. So we have the boundary, then we also have the ambience, that is the surrounding. Okay, so the boundary separates the ambience or the surrounding from from the system. Okay, and we have different types of systems when it comes to thermodynamics. We have steady states and the rest, okay, quasi-steady states and so on. So but what is important in this case is that, let's say this is the room, okay. Now the room has a shape of more like a cuboid, okay. So that means that's why we have the dimension to be in 6.0 meters by 15.0 meters by 3.0 meters. So which means the volume of the room, okay, the volume of the room will be what? Will be calculated from here. But first thing first, now let's first calculate the total power output. Now, like I said, firstly, okay, we will have to calculate the what? The total power output. Let's get the total power output. Now the total power output, that is the total power output, or you can also call it what? Output power, will be equals to the power output per student, okay, multiplied by the number of students in the class. So which means power output, we have power output per student, okay, multiplied by number of students, So what we are going to do now will be, so the total power, we are going to have the total power to be, so we have 200 watts per student, okay, multiplied by 10 students. So student will cancel student. So in this case, we are going to have the total power to be 2000 watts. So we have the total power to be 2000 watts. Now, also we need to calculate the energy in the room, because when we know that, okay, the number of students in the class, okay, is 10, okay. Now, and we have the total power to be 2000 watts, after which we calculated the what? After which we use the power output per student to multiply the number of students. Now, assume the initial temperature of the room is 20 degrees, okay. Remember, we want to find out the temperature of the room at the end of 1 hour. So which means energy, which is energy measures the product of power, that's the power, the total power, and what? Time taken. And we know we have here 1 hour, so the time is 1 hour, so we will have to convert it to what? To seconds. So which means total energy, we also need to calculate the total energy. So the total energy will be the product of power and time. Product of power and time. This is very important. So now we have the time to be 1 hour, which is 3,600 seconds. So the total power, which is what we calculated here, okay, we're going to plug the value for the value of the total power. We're going to plug that here. So we plug in the value of P, and we have 2,000 multiplied by 3,600. So in this case, the unit of energy will be the what? Joules. Okay, so all right, so this is going to be we have 3,600 multiplied by 2,000. Okay, that will be 7,200. So that will be 720. Okay, 000 0. Okay, so this is in joules. So the energy will then be 7.2 times 10 raised to the power of 6 joules. So this is the total energy. This is very important. We're going to need it for, so we've been able to calculate the total power. Now we have the total energy. All right. Now that's the total energy. Now, you know, transfer of energy in this case means energy conversion. You know, that is conversion from one form of energy into another form of energy. All right. So now also we are given here that assume the initial temperature of the room is 20 degrees Celsius. So let's say we have our starting temperature, which is the initial temperature. We are giving that to be 20 degrees Celsius. Okay. Now, then the dimension of the room. Now let's calculate the volume. Okay, volume of the room. Okay, we are given that its dimension, that's the dimension of the room, is given to be 6.0 meters by 15.0 meters by 3.0 meters. So we have volume of the room to be 6 multiplied by 15, then multiplied by 3. This will be in what? In cubic meters. All right, so we have 6 multiplied by 15. Okay, 6 multiplied by 15. Okay, 6 multiplied by 15, multiply by 15, then multiply by 3. That will be 270 cubic meters. Okay, so now, so we have, if all the energy remains in the air in the room, that means the energy remains in the air in the room. Now, none is added by an outside source, just like what I explained about a thermodynamic system. All right, so what is important here, we're giving the specific heat capacity of air to be this. So we're giving the specific heat capacity of air to be 837 joules per kilogram per degree Celsius. Okay, fine. Now we're also giving the density. Its density is about, that is the density of the air in the room, is about 1.3. Okay, density of air. Okay, 1.3 multiplied by 10 raised to the power of -3 grams per cubic centimeters. Okay, so what I will do is, let me convert the volume. Let me convert the volume into what? Cubic centimeters. So what we have here is, so the volume in cubic centimeters. So that will be, the volume in cubic centimeters will be 270 cubic centimeters multiplied by 10 raised to the power of 6. Okay, cubic, that is 200, that's 270 cubic meters multiplied by 10 raised to the power of 6 cubic centimeters over cubic meters. Yeah. Okay, so when this cancel out, so we're going to have 2.7 times 10 raised to the power of 8 cubic centimeters. Okay, that is the volume of the room. Volume of room. All right, so now, because we want to calculate the temperature of the room at the end of 1 hour, we've been able to calculate the total energy, and we've been able to calculate the total power, and we use the total power, you know, to calculate the total energy. And because we also need to calculate the mass of the room Yes, that's the mass of air in the room. Yes, so which means, so we that is mass of air in the room. Yes, mass of air in the room. So we know that from we know that density is mass over volume. Yeah, density is mass over volume. So we're going to have the mass to be equals to density, okay, because we are given here that the specific capacity of air is this, and its density is about 1.3 times, that's the density of air in the room, times 10 raised to the power of negative 3 grams per cubic centimeters. So this is the density of air in the room, then multiply by volume. Okay, that's volume of air. Okay, so we have the volume of air in the room. So now remember I said I have to, now it is important for me to convert this to into what? Cubic centimeters, because the density, I thought the density we are giving is in kilogram per cubic meters, but what we have here is in gram per cubic centimeter. So which means to be able to what, to be able to have all the units to be in CGS system of unit, which is a metric system of units. So that was why I decided to convert the volume from cubic meters into what? Cubic centimeters. Yes. So which means the mass of air, will now be 1.3, okay, multiplied by 10 raised to the power of, remember the density of air is given to be 1.3 times 10 raised to the power of negative 3 gram per cubic centimeters. So we have this in gram per cubic centimeters, then we are going to multiply by the volume in cubic centimeters, which is 2.7 times 10 raised to the power of 8 cubic centimeters. So this we cancel out. So now we have the mass to be in what? In grams. So let's find out what is 1.3 multiplied by 2.7. Okay, that will be 3.5. Okay, so we have 3.51 grams. Okay, 3.51 multiplied by 10 raised to the power of negative 3 times 10 raised to the power of 8 in grams. So the mass will be 3.51 multiplied by 10 raised to the power of what? 5 grams, because negative 3 plus 8, that will be what? 5. All right. So now let's now convert. Okay, let me convert it back into kilogram. So the mass in kilogram, that is, I'm going to divide this by 10 raised to the power of 3. Okay, so which means in kilogram the mass would be 3.51 times 10 raised to the power of, when we subtract 3 from 5, that will be 2. So this will be in kilograms, or we can have the mass to be that will be 351 kilograms. So this is the mass. Okay, now remember, what is the temperature of the room at the end of 1 hour? We calculated the power, okay, the total power, because the power output per student is given to be 200 watts. So there are 10 students in the class, so that means power per student multiplied by 10, and that will be what? 2000. Okay, then the total energy, because we know that power measures the rate of energy transferred, you know, the energy transferred in a material, or the energy expended or used up, you know, the energy used up, okay, that, or the rate at which energy is transferred, you know, through a material, that is energy over time. So power will then, now, so that means energy will be equals to power multiplied by time. So the product of power and time, so the total power, which is what we have here as 2000 watts, then we multiply by 1 hour, and we know that 1 hour is 3600 seconds. All right, so which is what we have here to be 7.2 times 10 raised to the power of 6 joules. Now we have the initial temperature to be what? To be 20 degrees. Okay, now then the volume of the room, okay, we converted the volume of the room from 270 cubic meters into 2.7 times 10 raised to the power of 8 cubic centimeters. You know, to convert from cubic meters into cubic centimeters, then you multiply the value by 10 raised to the power of 6. All right, so then, because to be able to calculate the temperature change, okay, you know, temperature change, now we have the energy. Okay, that's the energy in the room. Okay, so which means we're going to use the formula for calculating specific heat capacity, and that's what we have here. Yes, that's what we have here. So we just calculated the mass, okay, mass of the air in the room. All right, so now so in this case, to calculate now to calculate the temperature change, okay, to calculate the temperature change, so we're going to make use of heat, which is same thing as what? Energy. That's the quantity of heat, okay, equals to energy. That's the energy transfer. So that will be M multiplied by specific capacity, then multiplied by what? The temperature difference. So now we can express this in terms of MCE. Okay, so we have change in temperature to be E over MC. Now, this is the mass, okay, because the specific heat capacity is given in joules per kilogram per degree Celsius. So it is important to convert the mass from grams into what? Kilograms. Yeah. So now in this case, so we are going to plug in the values for E. So that is 7.2 multiplied by 10 raised to the power of 6. Okay. Then the mass, which is what? 351. Then multiply by this value, 837. Okay, so we have 351 multiplied by 837. Okay, that will be 293787. So the temperature change would be, now let me convert this into what? Standard form. So that will be, yeah, that will be 7200000 over 29, okay, 3787. All right, so 7200000 divide by 293787. Okay, so that will be 24. So that will be 24.51 degrees Celsius. 24.51 degrees Celsius. So with this now, we should be able to calculate the temperature of the room at the end of 1 hour. Now, when you say the temperature of the room at the end of 1 hour, now we know that change in temperature is final temperature minus what? Initial temperature. Okay, so which means to be able to calculate the final temperature, because we have here what is the temperature of the room at the end of 1 hour. So which means we're looking for the final temperature. So we know that the temperature, okay, that's the temperature of the room. The temperature, that is this new temperature, that's the change in temperature we just calculated, is 24.51 degrees Celsius. So which means the final temperature will be change in temperature plus the what? Initial temperature. And this final temperature is what they are asking, is what we are required to find out. What is the temperature of the room at the end of 1 hour? Okay, so at the end of 1 hour, that is, what is the new temperature when the initial temperature of the room is 20 degrees Celsius. So what will now be the temperature at the end of 1 hour, which is 3,600 seconds. Okay, so the final temperature will then be this value, okay, 24.51 added to 20 degrees Celsius. Okay, so when added together, okay, we're going to have 44.51 degree Celsius, and this is the temperature we are looking for, which is the final temperature, and also that's the temperature of the room at the end of 1 hour. Like I said, this aspect of thermal physics is the one that talks about energy transfer. So there is no mass transfer in this case, in the sense that we have the what? If all the energy remains in the air, in the room, and none is added by an external source. Okay, you know, that's why there's what we call closed system. We have open system and we also have closed system. When there's a transfer of mass across the boundary of a system, then that's in the case of what? Open system. But when there is no mass transfer, okay, across the boundary of a system, then we have what we call a closed system. And that's why the volume of the room is what is given in this dimension, which is 6.0 meters by 15.0 meters by 3.0 meters. The noblest pleasure is the joy of understanding. Bye-bye.